Children, let us see the solution for the question which I have assigned you. This is actually another school question paper, but it is good if you have a practice of different school question paper and you can have an exposure and you know the different levels of question, and very easily you will be able to crack your school question paper as well the board exam question. So that's a motive and that is an idea. And now the image below shows two examples of electric field lines. So this is uniform electric field line. This is electric field lines increasing over here. You can see here, keep on increasing. Here it is stronger. So the first one, both 1 and 2 arises due to single positive point. It is wrong because single positive point charge radially outwards. Radially outwards. Whereas the single negative charge, that is also wrong. That is radially inwards. So both are ruled out. Whereas the third one, electric field line, in first one is same everywhere, but the electric field becomes stronger as we move from left to right. Yes, it is stronger. So therefore C is the correct answer. D, of course, wrong. As you move from left to right, the electric field in both 1 and 2 becomes stronger. It is given. So that is wrong. So the first question answer is C. Hope you understand. We'll go to the next question. In the given region of electric field, there is no charge present. Look at the word, there is no charge present. If there is no charge, there is no flux. Q by epsilon naught, right? So no charge, so no flux. Is placed in this region of electric field. What is the requirement for the total flux of the container to be zero? For the container to be zero, what is that? The field must be uniform? No. The container must be symmetric? No. The container must be oriented in particular direction? No. There is no such requirement. The total flux of the container is zero, no matter what it is. So net charge is zero. So therefore, the total flux of the container is zero, no matter what is. Next question. So this is electric charge is uniformly distributed along a straight wire of radius 1 millimeter. So therefore, draw a Gaussian surface. That is Gaussian surface bigger radius. That is 50 centimeter. See, this is a straight wire of radius 1 millimeter. Now the charge per centimeter length of the wire is charge per centimeter. Charge per length. That is equal to capital. Or charge is equal to Q into L. Centimeter I have to give. So L is centimeter. Another cylindrical surface of radius 50 centimeter. Radius 50 centimeter. And length 1 meter. It symmetrically endorses the wire as shown in the figure. The total electric flux is equal to Q naught by epsilon naught. Instead of Q, I have to write it as capital Q. Into length is in centimeter, convert to meter, that is equal to 100 divided by epsilon naught. So this is the answer. 100 Q by epsilon. Next, fourth one. The capacitance of the capacitor C naught is connected to is the battery of V voltage, which charges the capacitor, and the capacitor is still connected to the battery without replacing the battery. A dielectric slab is placed, which we have already discussed. So here voltage is constant. V is equal to constant. Therefore, E doesn't change. E is same. When V is constant, C increases. Q is equal to CV over here. When C increases, Q also increases. So electric field between the plates of the capacitor rises wrong. Potential difference between the plates fall wrong. Total charge on the capacitor increases. That is the correct answer. Ability of charge, the capacitor stored charges remain the same. That is wrong. So hope you understand. So C is the correct answer. Next, read the following paragraph. Which of the following definitely not true when a conducting slab is introduced between the plates of the parallel capacitor? When the conducting slab is conducting slab, here when a conducting slab is introduced between the parallel capacitor, conductor. When you place a conductor between the plates of the capacitor, what happened to electric field? E is equal to E naught by K. So K is infinity. So therefore electric field will be equal to 0 when you place a conductor. But in the first case, it is given the electric field between the plate is maintained, which is not true over here. So therefore, this is the correct option. Capacitance of the capacitor increases, of course, because C is equal to K into C naught, hence increases. Charge stored in the capacitor increases or decreases. Sorry, charge stored in the capacitor may change or may not change. It's not possible. because here it is not given here whether it is connected to a battery or disconnected from the battery. But here the first case, whether it is connected or disconnected, the electric field between the plates is maintained is wrong. So therefore, this is the correct option. So next, here the charge Q on the capacitor varies with the potential as shown in the figure. The area under the graph, half into base into height. So that's equal to half into Q into V. That's equal to energy. So D is option. Next, in a parallel plate capacitor, the capacitor increases from 4 microfarad to 80 microfarad. So we know that this is C naught and this is C. So C is equal to K C naught. So therefore 80 is equal to K into 4. So therefore K will be equal to 20. So 20 is the option. And this question, children, this is actually interdisciplinary question based on Wheatstone principle. In current electricity only, we're going to study. What if you know Wheatstone principle? You can correlate the same thing. If the ratio of the capacitance are going to be equal, then there won't be any contribution due to this middle capacitor. So therefore, you have to redraw the circuit like that. This is NDA, this is C, this is C. Then similarly, this is end B, this is C, this is C. These two are connected in series. So therefore, effective capacitance is equal to C by 2. Again, these two are connected in series, effective capacitance C by 2. So C by 2 and C by 2 are connected in parallel. So therefore, the effective capacitance is equal to C. So C is the answer. So hope you understand, children. Next. Determine the electric field at a point P along the axial line of electric dipole or dipole moment P at a distance x from the center of the dipole. This is a derivation. Refer your green book or your class notebook and then write. This is axial line. What will be the electric field due to a short dipole? That is 2 kp by x cube. Two positive charges Q1 and Q2 are lying along the straight line separated with distance 2 meters. Find the location along the straight line joining the two charges where if a positive charge Q3 is placed, it experiences zero resultant force. So let us suppose Q3 is placed at a distance x from Q1. So the remaining is going to be 2 minus x. Then you can say K into Q1 into Q3 divided by R, that is x, should be equal to that of K into Q2 into Q3 divided by 2 minus x. So therefore K get cancelled, Q3 get cancelled. So therefore what is Q1 here? 2. So therefore I am taking this as 2 by x is equal to 4 by 2 minus x. The whole square I mean. So therefore I can take square root on both the sides after reducing it. So when I take square root on both the sides, so 1 by x is equal to, this is root 2 divided by 2 minus x. Now cross multiply, 2 minus x is equal to root 2x. Therefore, x plus root 2, x is equal to 2. So therefore, x is equal to 2 by 1 plus root 2. So 2 by 1 plus root 2 is 2 by 2.414. So that will be equal to 0.83 meters. So 0.83 meters from Q1. That's the answer. 0.83 meters from Q1. So hope you understand this, children. We will go to the next one. Right. This is actually MCQ, no? So this has been scanned in a different order. That's not a problem. Fifth question we'll see. The decreasing order of the electrostatic potential. So the first one, what is electrostatic potential? KQ into minus Q divided by R. Second one, KQ square divided by R. Third one, K into 2Q square divided by R. Fourth one, KQ into, see fourth one. Fourth one, K into minus K into 2Q square divided by 2R. So 2 get cancelled, so minus KQ square by R. Here also it's minus KQ square by R. So A part is KQ square by R and D part is also KQ square by R. So A is equal to D. Right? A is equal to D, no? So trace out where A is equal to D. One and only option. That's all. Got it? And which is the largest one? K into 2Q square by R is the largest one. So that is C is the largest one. So here C is the largest. So option is D. Okay, next. Assertion reasoning. A charge 3 microcoulomb is moved from point A, that is on the equatorial line of dipole. This is equatorial line of dipole. 90-degree turn and check. To the center of the dipole along the path as shown in the figure, for this motion, work done by the force will be zero. Of course, because equipotential surface, because the electric potential of the equatorial line of dipole is zero, therefore work done is zero. That's perfect answer. Electric force is a conservative force. Yes, it does not depends upon the path. Here it is given. It has been taken from here to here. Say here, been taken from here to here. However, it is taken, work done. Due to the electric force, this is a conservative force. Independent of the path it follows, potential at point A is equal to potential at point 2. So therefore, potential difference is equal to 0. So hence, A is the correct option. Next. P and Q are concentrate conducting shells connected to each other by conducting wire. The total charge of 10 coulomb is given to the system of 2 concentric shells. So now let us suppose this is A and this is Q1. And this is B and this is Q2. But of course, it is given Q1 plus Q2 is equal to 10. But though Q1 plus Q2 is equal to 10 over here, how much charge will settle on each cell? Because it's connected by a conducting wire, it is given. If it is connected by a conducting wire, potential is going to be same. So Vp must be equal to Vq over here. First of all, we'll find out what is Vp. Vp is equal to KQ1 divided by A. But what is VQ is equal to? VQ potential is nothing but due to inner charge potential plus outer charge potential. So therefore, I can write it as KQ1 by B plus KQ2 divided by B. So therefore, VQ will be equal to K by B, take it out, Q1 plus Q2. Now, what is Q1 plus Q2? It is already given now 10. So therefore, 10K by B, that is VQ. I know VQ, I know VP. That's all. Correlate both. Why to correlate? Because potential should be same as is connected to the wire. So KQ1 by A is equal to 10K. K into 10 divided by B. Now KK get cancelled. So Q1 is equal to A by B into 10. What is A? 0.4. What is B? 6. So therefore, I can write here as 0.4. That is 4 by 6 into 10. That is equal to 3 by 2 into 10. So Q1 is nothing but 30 by 2. Q1 is equal to 30 by 2. If Q1 is equal to 30 by 2, right? 4 by 6, so that is equal to 2 by 3. So 20 by 3, I'm sorry. Q1 is equal to 20 by 3. See? A by B, no? So what is A by B? Here. What is A given? 0.4. B, 6.6. So 0.4 by 0.6 is 4 by 6 into 10. So that is equal to 2 by 3 into 10. So that's equal to 20 by 3 is Q1. So if Q1 is equal to 20 by 3, so what is Q2? Q1 is equal to 20 by 3. Therefore, Q1 plus Q2 is equal to 10. So therefore, Q2 will be equal to 10 minus 20 by 3. That is equal to 10 by 3. So therefore, Q1 is 20 by 3 and Q2 is 10 by 3. Good. Hope you understand this. Little you need to think and then do it. So when you add both, you will have to get it as step. Yes. Okay, right. A positively charged ball hangs from a string. A non-conducting ball is brought near the ball A. Non-conducting ball is brought near the ball A. Ball A is seen to be attracted to ball B. If it is getting attracted, you can say ball A, it may be due to induction or it may be due to negative charge. So, Give reason why it is not possible to determine whether the ball B is negatively charged or neutral for sure for the above experiment. I've already told you here, if it is going to be attracting, it is not the reason it is only due to the negative charge. It is that reason that it can be due to charging by electrostatic induction. So hope you understand that. Suggest any one additional experiment with ball B. So ball B, I'm going to take fully ball B. Required to determine whether the ball B is negatively charged or neutral. So if ball B is going to be neutral, and if I'm bringing any other negative, negative, what does it do? Ripple over here. The ball B is negative, I'm going to bring a neutral one. If I'm going to bring a neutral one. So what will happen? This dielectric polarization takes place and it can attract this. So therefore, negative charge or repulsion is the surest test. So you can, if you want to just test the same thing, whether it is negatively charged or whatever, only repulsion can, give you correct answer. Okay. So you can also go through from the NCERT textbook the same answer. That means the conceptual answer you'll be able to get it. Okay, children. A thin rod of length L and uniformly mass density of mu kilogram per meter. That is nothing but mass per unit length is equal to mu. And linear charge density, that is equal to Q by L, is equal to lambda. A uniform electric field is set up in the direction perpendicular to the length of the rod. So this is the rod. This is a thin rod and it is charged. Electric field is set up over here. So when it is electric field is set up, it gets accelerated. Due to acceleration, so what will happen? It undergoes displacement over here. So therefore, we know that V square is equal to U square plus 2AS. V square is equal to 0 plus 2 into A into S. So V is equal to square root of 2AS. Of course, it gave displacement is given as 1 meter somewhere here. It is given 1 meter. So therefore, V will be equal to root of 2A only. Okay, right? V is equal to root of 2A. So how do you write? A is nothing but 2 into F by M. So that is equal to root of 2 into QE by M. Okay, right. What is Q by M? What is charge per? This is mass per unit length is given. So therefore, QE by M, right? So we know that lambda is equal to Q by L. So therefore, Q is equal to lambda L. So I can write here lambda L. So that is equal to 2 into lambda L E by M. What is L by M? L by M is mu, 1 by mu. So 2 into lambda into E divided by mu. So V is equal to root of 2 lambda E by mu. That is the answer. It's a very interesting question. You can learn that. Okay, children. Next. Given below is the representation of equipotential lines in a given electric field region. Determine the strength and direction of the electric field. Now, point one, you take now 40 to 20. What is the distance? You have to write it as 1 centimeter. E is equal to minus dV by dx. Mod of E is equal to dV by dx. So that will be equal to 40 minus 20. That is equal to 20 divided by 1 centimeter. So that is equal to 20 into 10 power minus 2 becomes plus 2 volt per meter. And what about the second point also? Second point, what is the distance here? 0 to 20 voltage, that is 1 centimeter. So second also 20 divided by 1 centimeter. Second one also. So that is equal to 20 into 10 power 2 volt per meter. Okay, this is 1 centimeter only, no? So that is why. Okay, so now 1 centimeter from the y-axis, if you want to take, this is 1 centimeter, this is 1 centimeter. So from the y-axis, so therefore that is 2 centimeter from the y-axis. If you take the, so 20 by 2 centimeters, that will be equal to 10 into 10 power 2 volt per meter. So you have to check on that from where it is being asked. Okay. So and then electric field, if potential keeps on decreasing, so then the electric field increases. Therefore, the electric field direction is towards positive. x-axis. So E into I cap. So hope you understand, children. Thank you, children. So likewise, you can learn the same thing